Hello everyone, and welcome to another mini Sky Tonight. So I had a viewer ask me about nebulas and how we get all the beautiful bright colors that we see in the nebula. And indeed, nebula are quite beautiful. In fact, if anything, if you are kind of bored with this topic and don't want to invest in it per se, at least you can look at pretty pictures because nebula pictures are really pretty and they're fun to look at. So let's kind of dive into how we get nebula and talk about stars and the stellar life cycle, because believe it or not, nebula come from stars, and the elements that are used inside nebula to give us the beautiful colors come from stars. So let's start from the beginning. So stars come from areas known as molecular clouds. They're basically areas of gas, dust, and other types of materials that are found inside our galaxy. And over time, clumps of the material start attaching to other clumps, and those clumps start gaining enough mass to where they produce gravity. And anything that has gravity will start to attract other things. So all of a sudden, this bigger clump will start attracting another smaller clump and another smaller clump until eventually it starts getting enough gas clumps to where it starts heating up. And it starts to spin because it's starting to rotate as clumps are being rammed into it. And as it's starting to heat up, it goes into a phase known as a protostar. So it starts heating up. It kind of looks like a little heated sphere inside a big, huge blob of gas. And there's a disk around it of more material. This is known as an accretion disk. So as more material gets into the star and gets into the star, eventually the star starts to become stable, where gravity that's pulling material in and the heat that's pushing the material out reach an equilibrium. And then basically the star starts to do nuclear fusion, where it produces its own light, heat, and energy. And it puffs out all the excess material, creating the beautiful star, and then maybe a few planets that go around the newly formed star. And you can get three different types of stars. You can get brown dwarf stars, which are really, really, really low mass stars that are just whatever little material they could get, and that was it. Then you get low mass stars, which is similar to our sun. And then you can get high massive stars, which is about 8 times more massive than our sun and higher. In fact, I think the most massive star that we've come across so far is roughly around about 50 times the mass of our sun. So what's going inside stars that produce all the elements that we see? Well, hydrogen is the most abundant element in our universe. And so many stars are formed with hydrogen. And so during the nuclear fusion process, they try to fuse some of the lighter elements to produce light, heat, and energy. So 2 hydrogen atoms ram together to produce a heavy hydrogen and a single hydrogen, plus a neutrino and gamma rays and light, heat, and energy. And then those hydrogen atoms ran together to produce a light helium and a hydrogen atom, and then those ran together to produce a standard helium. And then you start fusing further and further to start getting carbon, nitrogen, oxygen, and so on. So believe it or not, all of the elements in our universe are created in stars. In fact, if you look at every single element on the periodic table of elements, not the ones down on the bottom one, those are the funky ones that are usually created in labs. I'm talking about the naturally formed elements on the periodic table. All of those elements were created in stars. So all of the elements that you see here on Earth were once inside stars. So we are but such stuff that stars are made out of. And I always think that's really cool. But nonetheless, as the fusion process keeps going, eventually it's going to start running out. And this is where we start getting into further in the stellar life cycle. So for low mass stars, we don't want to include brown dwarf stars because they eventually just fizzle out because they have barely enough just to keep burning, and so they just fizzle out. But for low mass stars, since they have a little more mass, they are able to keep fusing and fusing. They start fusing into carbon, nitrogen, and oxygen, and so on. Once they start fusing helium, so they go from hydrogen to helium, helium to nitrogen, nitrogen to carbon, carbon to oxygen, and so on. So once they start fusing helium, they start to swell up, and the outer shell of the low mass star is your hydrogen shell, and it's trying to fuse helium on the inside to try to still keep going. And then it goes into its next stages of whether it becomes a planetary nebula or a different type of nova. Now for your high mass stars, they also go into a red giant phase, but they go into a red supergiant phase because they're much bigger and they contain more mass. And they keep fusing and fusing and fusing material. And they can fuse all the material down to iron. Now, for high mass stars, iron is the kiss of death because iron is one of the first elements that are metallic that when you try to fuse it together with all the electrons around iron, since it's a electrically conductive material, it doesn't like to fuse at all. It takes more energy to fuse iron than you get out of it. So this literally becomes a cascade event where basically it starts producing other materials known as neutrons, and it basically becomes a cascade event to where it eventually goes kaboom, where all of a sudden this big huge supergiant star just collapses on itself one last time and then explodes epically outward in what is known as a type 2 supernova. Those are the big booms that we see, to where you can get a supernova remnant with a neutron star or a pulsar, or you can start getting a black hole. But what we're interested in is the nebula. Now, keep in mind we started with a nebula and we end with a nebula because our galaxy is a great recycler. So the death of stars is sometimes what is used then to create new stars. So some of the type 1 super A nova remnants plus the planetary nebulas and the supernova remnants, all of them, that type of nebula would mix with molecular clouds nearby, creating a new molecular cloud, and those molecular clouds create new stars, and so on. So our galaxy recycles, and so should we. So when we are looking at these nebulas, keep in mind there's a little bit of trickery going on, but not to deceive you. So when we compare images from NASA versus a natural photo, just a standard straight image compiled. So the way astrophotography is done, meaning doing photography of the sky, you have to take an image and it kind of looks kind of gray and white. But once you start combining it with other images, it starts to show a color depending upon what types of filters you use. Now, in astronomy, there are 3 different types of filters. There's a red, blue, and a green. And if you compile those, you get the beautiful image that you see on the right. So this image on the right is the Eagle Nebula, and you see all these beautiful hues and colors and things like that. You see all these beautiful red kind of hues and things. But the image on the left is what's produced by NASA. So how does it get all those colors? Well, they use also ultraviolet light, they use infrared light, and they combine all of those from different satellites to create the image you see on the left. And they sometimes use what is known as false coloring to indicate different types of materials to show you what's going on. So it's not necessarily to deceive you per se, it's to show you, hey, there's more depth to this image than originally meets the eye, because if you look on the image on the right, you can't really see a whole lot going on in the inside, but the image on the left, you see the beautiful concavity that some of the stars on the inside are creating. So being able to do some of this false colored imaging plus combining different wavelengths that the normal telescope can't give you allows you to see the image in different light, so to say. Also, keep in mind different wavelengths. Like I mentioned, in NASA, they often combine like infrared and ultraviolet light too, but sometimes you can use X-ray, you can use gamma ray, and so on, and compile those to get beautiful images. So in the case of the Eagle Nebula, the image on the left is basically the combination of all the visual spectrums, and the image on the right is just infrared, completely infrared. And the great thing about using infrared is because infrared shows you stars that you could not see normally inside the nebula, because stars naturally produce heat, and so we're able to see the stars through the dark nebula. Now the nebula is relatively cold, so by using infrared light, we're able to see the stars that are on the other side of the nebula. So with that in mind, let's look at the different types of nebula, because we kind of discussed it when we talked about the stellar cycle. So let's look at some of the different types of nebula that you can see. So the first example is what is known as a mission nebula. It's basically high temperature gas, where the stars inside the gas are literally heating up the gas to high temperatures to where they emit light. Kind of like a neon light. So when you look outside on the neon lights on buildings, not the electrical ones which basically use LED lights per se, but the traditional neon lights with those tubes on the outside, it's basically there is a gas on the inside of the tube, and it's mostly often used as neon, but they sometimes use different types of gas to give it different colors. And the electricity that is going through the tube is causing energy to go into the gas, and naturally that energy wants to dispel, so it produces light. And hence why we have the beautiful neon signs we see on businesses and road signs and things like that. Well, that's what's going on here with the emission nebula. The light from the stars inside the nebula is heating up the gas, and that gas doesn't want to contain all this energy, so it produces it out in terms of light. A great example of emission nebula is the Orion Nebula. So the beautiful white and pink hues that you see in the emission nebula is because of the stars that are inside the nebula, and it's heating up the gas. Another type of nebula is known as reflection nebula. It is basically kind of like what it sounds. It literally is light reflected from the stars. So it acts like a mirror. So the light from the star is on the outside, and the light is bouncing off of the clouds, and we get to see those different colors. And these usually tend to be blue because blue light is easy to scatter. So hence why we have a blue sky. Light from the sun is being scattered through our atmosphere, and blue light scatters really easy. And since it scatters really easy, we see a blue sky. Same thing with reflection nebula. Since light easily scatters inside the nebula because it's filled with gas, blue light is usually what we see being reflected. A great example of this is the Trifid Nebula, where on the top part you have an emission nebula, and on the bottom part you have the reflection nebula. As we discussed earlier, the third type of nebula is known as a planetary nebula. This is the result of a low mass star dying, similar to what will happen when our sun dies. As I mentioned earlier with the stellar cycle, our sun will keep fusing hydrogen, and it'll try to go into helium, into nitrogen, to carbon, and so on. But eventually, it's not going to have enough mass to keep trying to fuse, so it will collapse down to a tiny little star known as a white dwarf star. And it will puff up its outer layers into this like cosmic cocoon around the star, or a cosmic ash ball. I like to call it basically a cosmic tomb, so to say, where the tiny little star in the center is the remnant of the star, and you have this beautiful outer cocoon outside the star. In fact, a great example of this is the Ring Nebula. So in the center of the image there, that little tiny white star in the center there is the stellar remnant of the star that once was. And the beautiful ring that you see around it is the puffed out outer shell. Now, it's not planetary nebula in terms of like, oh, there's planets out there, but the fact that it kind of looks like a planet, especially when you look at it from a low-res telescope, and it kind of has disc-like shape. So they named it for the shape, not necessarily if it has planets or not. The next type of nebula is referred to as dark type of nebula. So these are like really dark and cold gas and dust that's incredibly thick, where light cannot be shined through. And you can see a great example of this is known as the Horsehead Nebula, where you have this beautiful pillar that literally very few stars can pierce through. In fact, some of the stars you can see from the Horsehead Nebula are often stars that are in front of the nebula and they don't reflect. And of course, the last type of nebula that you can see is what are known as supernova remnants. They are the result of a high mass dying star. Where a planetary nebula was the result of a low mass star dying, these are the results of a high mass star dying, where basically they go kaboom, and they're very chaotic because literally it's an explosion in space. And they don't have any standard structure, where many of the nebulas prior have these wispy structures and things like that. These are just pure chaos. An example of this is the Crab Nebula, where the term pulsar came from the Crab Nebula, where we discovered inside the center of the supernova remnant a star that would have a radio signal that would go really, really fast. And that gave us the term pulsar because it pulses over the course of time. So these are the different types of nebula. So let's look at, from the standard images, what these colors represent. So usually colors represent what types of elements they are, like the stars that are around them, and if they're scattering. So many of your hydrogens from a standard image give you your pinks and your light reds and your magenta colors, whereas in your oxygens are often your teals, light blues, and sometimes greens. Your deep greens are your sulfurs. Your oranges are your heliums, or sometimes if there's an orange star nearby that's lighting up the gas and the dust, it gives that a orange hue. Deep reds and purples are your nitrogens, and browns are just excess gas that's being lit up. So like, for example, in the supernova remnant, those brown tinges is just gas and dust that's intermixed, and it gives that a brown color. And of course, blue can either be like nearby blue stars or scattering inside the nebula. So this is where we can get some of the different colors of it. But these are some of the details of it, but honestly, beautiful images are still beautiful to enjoy. Nonetheless, if you have any topics that you would like for me to cover over, or if you have any more details you would like to learn about it, leave it down in the comments below. If you'd like for me to cover over other types of means, like doing a live telescope presentation or doing a live Sky Tonight presentation, let me know as well. And until next time, stay safe, stay healthy, and as always, never stop learning.